This video briefly examines the mathematical details of Lagrange points, which are special points in the presence of two large celestial bodies. In the interest of time, we give a general outline of the results without showing every little detail. So let's begin by assuming we have 2-point masses with circular orbits around the origin. The magnitudes of the two masses are m1 and m2 respectively, and they're a distance capital R apart. It's not mathematically necessary, but let's assume the first mass is bigger, so m1 is bigger than m2. We represent this graphically by making the disk on the left bigger than the disk on the right. And at time t equals 0, we locate the first mass at x1 on the x-axis and the second at x equals x2. So the first thing we want to do is figure out the angular speed of the rotation. We're going to call that omega. Since the objects orbit their common center of mass, we can deduce that x1 is minus m1r over the total mass, and x2 is m2r over the total mass. The center of mass is simply the weighted average of x1 and x2 weighted by the masses. And we can parameterize the circular orbits with sines and cosines, and plugging those parameterizations into the equations of motion, we can easily compute omega. Again, we're omitting all the details here to avoid cluttering up the presentation. Please note that over dots indicate differentiation with respect to time, and 2 over dots indicates a second derivative with respect to time. Now let's add a satellite to the system. This will be a third mass that's so small that it doesn't alter the circular orbits of the original two masses. Its position will be at the coordinates x, y, and of course x and y will both change with time. Now, to study Lagrange points, it's convenient to use a coordinate system that rotates counterclockwise around the origin along with the two original masses. In that coordinate system, the first mass is fixed at x10 and the second is fixed at x20. The governing equations for the satellite can be determined with Newton's universal law of gravitation, but we have to be careful to include the centrifugal and Coriolis terms that appear because we're using a rotating, non-inertial reference frame. The omega squared terms in the two differential equations are the centrifugal terms, and the omega terms are the Coriolis terms. Now, it's nice to clean up the problem by hiding all the physical parameters by non-dimensionalizing the problem. So to do that, let's first let m2 be mu times m1. Now, since we're thinking of m1 as the larger mass, we're going to assume that mu is less than 1. Also note that mu has no units. We also scale all distances, like x1, x2, x, and y, by r, the distance between the two bodies. And omega has units of 1 over time. So we're going to scale time by the square root of 1 plus mu over omega. The inclusion of the dimensionless quantity square root of 1 plus mu is a mere convenience that makes the coefficients of x double dot and y double dot equal to 1. So please note that these equations are completely dimensionless. Now, Lagrange points occur where there's no net force acting on the satellite. This can be useful in practice because parking a satellite or a telescope at a Lagrange point means that it requires little fuel to maintain its position. Now, we want to find Lagrange points, and then we want to investigate their stability. Okay, so what we mean by that is if a satellite were to sit exactly at a Lagrange point, then it won't move. But if its position deviates ever so slightly from a Lagrange point, then we want to know what to expect. If the trajectory tends to move away from the Lagrange point, then we'll say that that point is unstable. Now, before solving for the Lagrange points, let's look at some pictures that'll suggest what we expect to learn from the mathematics. In this picture, we use mu equals 1/3 because that makes it easy to see what's going on. If we use a more extreme value for mu, then it's harder to see some of the details. Here you're looking at a vector plot of the acceleration field acting on the satellite. If the satellite is close to either of the two black masses, then it's attracted to them, as one would expect. However, far away from the two masses, the centrifugal force pushes the satellite away from the origin. Now, this is a plot of simply the magnitude of the acceleration. From the legend, we can see the acceleration is 0 where the graph is very dark. We also see that acceleration magnitudes are only plotted from 0 to 3 because the accelerations grow very large near the two orbiting masses. Now, looking at the dark spots, we might think the acceleration is 0 in about 3/4 of a ring on around the left side of the larger mass. but there are actually only 5 points where the acceleration exactly vanishes. These are the 5 Lagrange points labeled L1 to L5. Now, if we zoom in by restricting the range of acceleration values to 0 to 1, remember it was 0 to 3 before, then we can see a little more clearly that the graph is darker at the labeled Lagrange points than it is in most of that 3/4 ring. So this gives us a sense that the acceleration is small in that 3/4 ring, but not necessarily 0. We also want to note that L1, L2, and L3 all lie on the x-axis where y is 0, and L4 and L5 are off the axis, but they're symmetric with respect to the x-axis. Now, to find the Lagrange points mathematically, we're going to set all the derivative terms in the two differential equations equal to 0. To find L1, L2, and L3 in particular, we're going to set y to 0 because they live on the x-axis. This gives a single complicated equation in x that we have to solve numerically using Newton's method or some other suitable method. The graph shows what the function on the left-hand side of the equation looks like for mu equals 1/3, and you can see the 3 intersection points that correspond to L1, L2, and L3. Now, what's really interesting is you can find L4 and L5 exactly. To do this, we choose x to make the two big denominators in the two differential equations equal to one another. Again, omitting all the details, a little bit of high school algebra shows that x is 1 minus mu over 2 times 1 plus mu. And once you know x, you can plug that back in and go back and solve for y, which turns out to be plus or minus the square root of 3 over 2. Again, these are dimensionless quantities. Plotting these with the two masses, you can actually see that the two bodies, along with L4 and L5, form equilateral triangles. Now, the picture is not a proof of that, but it's not that hard to work out by hand, that those are in fact equilateral triangles. All right, so now that we know where the Lagrange points are, we want to study their stability. To do so, we're going to convert the original pair of second-order equations to a first-order system in 4 dependent variables: the original x and y, the position of the satellite, along with the x and y velocities of the satellite that we're going to call v sub x and v sub y, respectively. To determine the stability of a Lagrange point, we linearize the first-order system at that point and compute the eigenvalues of the resulting Jacobian matrix. Since we know L4 exactly, let's begin with it. Here we see the linearized system of equations, and remarkably, we're able to solve for the eigenvalues exactly in terms of mu. The expression's a little bit complicated, but not too bad. If any eigenvalue has a positive real part, then solutions near L4 will tend to move away from that Lagrange point, and it will be unstable. Eigenvalues that have a negative real part correspond to solutions that will move toward the Lagrange point. They'd be attracted to it. And eigenvalues with 0 real part will tend to move around the Lagrange point without being attracted to it or repelled by it. Now for L4, all the eigenvalues are purely imaginary if mu is less than about 0.04. So here's a plot of the eigenvalues, their real and imaginary parts, as a function of mu. You can see that beyond mu about 0.04, 2 of the eigenvalues have positive real parts, so L4 is unstable. So in other words, the smaller mass has to be at least 25 times smaller than the big mass for L4 to be stable. So if M1 and M2 are similar in magnitude, then L4 is not a stable Lagrange point. Of course, the behavior at L5 is very similar. So now let's turn our attention to L1, L2, and L3. Remember, they had to be determined numerically, so the eigenvalues are also determined numerically. Here you can see from the plots of the eigenvalues as a function of mu that there's always eigenvalues with a positive real part. So all 3 of these Lagrange points are unstable. Note that for very small mu, the real parts for L3 are relatively small, so we might expect it to take longer for solutions to move away from L3 than it takes for them to move away from L1 and L2. So let's look at a concrete example, and let's take mu to be 1 over 81. This is motivated by the fact that the Earth is 81 times larger by mass than the Moon, and by the fact that mu equals 1 over 81 is sufficient to give us stable L4 and L5 points. So here's a plot of the 5 Lagrange points. And what we want to do now is examine the stability. So we want to imagine we choose starting positions near each of the 5 Lagrange points. And we also want to assume the velocity is 0 there, because we have to choose something. And what we want to do is let time go and see what happens to the resulting trajectories. So the satellite near L1 moves in a dramatic fashion, and it traces what looks like a five-petal flower around the Earth. The satellite near L2 moves quickly to leave the chosen field of view. Near L3, the satellite appears to be moving away from that Lagrange point, but it seems to do so relatively slowly. Again, has relatively small positive real parts for its eigenvalues. Near L4 and L5, the motion stays close to the Lagrange points, but they don't asymptotically approach either the Lagrange points, and they don't seem to move away. They just sort of float around L4 and L5. Now, we're not used to looking at things in a rotating frame of reference. So what we want to do is give an animation in the non-rotating inertial frame of reference where we'll see the moon and the Earth moving, and we want to look at the trajectories there. So here we can see the moon moving around the Earth in a circular orbit. The Earth is moving too, but because 1/81 is pretty small, you can't really see too much. You can see the purple point moving quite a bit. It started near L1, so it's moving a lot. The blue one has already left the field of view, though at the end of the video, you'll see it come back in. The green dot started near L3, and it's still pretty close to L3, but it is moving away. The red and yellow dots are still close to their Lagrange points, and they're not going to move far away. So again, you can still see the purple one tracing out what in the non-inertial reference frame looks like a five-petal flower that's moving around the Earth quite rapidly. The green one is moving now farther away from L3. It's getting close to the red point. But the red and the yellow stay close to their original homes. You can see the green one's getting close to the moon now. And here it's going to leave our field of view, but there comes the blue one back into view. Now, before we finish, we want to emphasize that the animations we just looked at are just one set of trajectories that are possible, right? It all depends on what initial conditions you choose. So if you change the initial positions of the satellites, you can get dramatically different behavior, as you can see in these 6 different shots. You can see the one near L1 does dramatically different things. It might trace a sort of flower pattern. In the picture in the top middle, it seems to just zoom around the moon quite a bit. The one at L2 also does very different things. It's blue. The first two in the top row, it just immediately leaves the field of view. In the one in the top right, you can see it's going to zoom around the moon a whole bunch. Actually, it does that in the next 3 pictures. So very different things happen. The green one starts near L3, and you can see it does very different things depending on the small details of where it started. At L4 and L5, the yellow and the red ones, they do tend to hang out around those 2 Lagrange points, but they do trace some very different sorts of patterns, right? Which is, I think, very interesting.